Welcome to today's paper reading. Today's paper is titled, A Survey of NL2SQL with Large Language Models. Where are we, and where are we going? This paper, published in the Journal of LaTeX Class Files, surveys the advancements in NL2SQL techniques powered by large language models. Authored by Xinyu Liu and colleagues from the Hong Kong University of Science and Technology, Guangzhou, Renmin University of China, and Tsinghua University, the survey provides a comprehensive review of the NL2SQL lifecycle and discusses future research directions. The abstract highlights the importance of translating natural language queries into SQL queries, known as NL2SQL. This translation significantly reduces barriers to accessing relational databases and supports various commercial applications. The performance of NL2SQL has been greatly enhanced with the emergence of large language models, LLMs. This survey provides a comprehensive review of NL2SQL techniques powered by LLMs, covering its entire lifecycle from four main aspects: model techniques, data collection and synthesis, evaluation methods, and error analysis. The survey also discusses the research challenges and open problems of NL2SQL in the era of LLMs. Figure 1 provides an overview of the lifecycle of the NL2SQL task, which includes four main aspects: model techniques, data collection and synthesis, evaluation methods, and error analysis. The figure highlights the importance of tackling NL ambiguity and under-specification, the need for high-quality training data, and the necessity of comprehensive evaluations to optimize and select models for different scenarios. Additionally, it emphasizes the role of error analysis in identifying model limitations and guiding the evolution of NL2SQL models. The introduction of the paper focuses on natural language to SQL, NL2SQL, a technique that converts natural language queries into SQL queries. This conversion is crucial for lowering the barrier to accessing relational databases, making it a key step in democratizing data science. The technique supports various applications such as business intelligence and customer support. Recent advancements in language models have significantly extended the frontiers of research and application in NL2SQL. Database vendors have also evolved their strategies to include NL2SQL solutions as a necessity. Therefore, understanding the fundamentals, techniques, and challenges of NL2SQL is important. The NL2SQL task involves converting natural language queries into SQL queries executable on a relational database. This process is challenging due to the ambiguity and under-specification often found in natural language. When humans perform this task, they first understand the natural language query, then link it to the database schema and content, and finally translate it into SQL. Key challenges include the uncertainty of natural language queries, the complexity of database schemas, and the difficulty of translating natural language into SQL. These challenges highlight the need for robust NL2SQL solutions. Figure 2 illustrates the challenges associated with the NL2SQL task. It highlights the ambiguity in natural language queries, the complexity of database schema and content, and the one-to-many mapping between natural language and SQL queries. These challenges include lexical and syntactic ambiguity, under-specification, user mistakes, complex relationships among numerous tables, similarity in column names, domain-specific schema variations, large and dirty values, free-form NL versus constrained SQL, multiple possible SQL queries, and database schema dependency. Figure 3 illustrates the evolution of NL2SQL solutions from the perspective of language models. It categorizes the challenges of NL2SQL into 5 levels, each with specific challenges. The evolution is described in 4 stages: rule-based, neural network-based, PLM-based, and LLM-based. The figure highlights the emergent capabilities of LLMs, which have significantly enhanced natural language understanding and shifted the focus of challenges towards the database layer. Figure 4 categorizes the roles of pre-trained language models, PLMs, and large language models, LLMs, in natural language to SQL, NL2SQL, tasks. It highlights that LLMs, characterized by superior language understanding and emergent capabilities, can perform NL2SQL tasks using prompts. In contrast, PLMs typically require pre-training or fine-tuning to achieve similar performance in NL2 SQL tasks. The paper outlines the key modules of NL2 SQL solutions powered by language models, particularly PLMs and LLMs. The pre-processing stage includes schema linking, database content retrieval, and additional information acquisition, which enhance the model's inputs. The core of NL2 SQL translation involves encoding strategies, decoding strategies, and task-specific prompt strategies, which convert natural language queries into SQL queries. Post-processing strategies refine the generated SQL queries, including SQL correction, output consistency, and execution-guided strategies to ensure accuracy and meet user expectations. Figure 5 provides a comprehensive overview of the key modules involved in NL2 SQL solutions within the era of large language models, LLMs. The figure highlights the importance of pre-processing steps such as schema linking and database content retrieval, which are crucial for identifying relevant tables and columns, and retrieving necessary database contents. It also emphasizes the core NL2 SQL translation methods, including various encoding and decoding strategies, which are responsible for converting natural language queries into SQL queries. Additionally, the figure outlines post-processing techniques, such as SQL query correction and ensuring output consistency, to refine the generated SQL queries and meet user expectations more accurately. This overview underscores the integrated approach required for effective NL2 SQL solutions in the context of advanced language models. The pre-processing step in NL2 SQL translation is crucial for identifying relevant tables and columns, retrieving database contents, and enriching context with domain-specific knowledge. Schema linking methods include string matching, neural networks, and in-context learning. Database content retrieval strategies involve string matching, neural networks, and indexing. Additional information acquisition focuses on domain knowledge, few-shot examples, and similarity-based retrieval to enhance the NL2 SQL model's understanding and performance. The NL2 SQL translation methods discussed in this section can be broadly categorized into three main strategies: encoding, decoding, and task-specific prompt strategies. The encoding strategies include sequential encoding, where both the natural language and the database schema are treated as sequences of tokens; graph-based encoding, which represents the natural language and database schema as graphs to capture complex relationships; and separate encoding, where different parts of the natural language are encoded separately. Decoding strategies involve converting the encoded representations into SQL queries and include greedy search, beam search, and constraint-aware incremental decoding. Task-specific prompt strategies focus on optimizing the SQL query generation process and include chain of thought, decomposition, and the use of intermediate representations to bridge the gap between natural language queries and SQL. Figure 6 presents a taxonomy of NL2 SQL translation methods categorized by their design choices. The primary encoding strategies include sequential encoding, graph-based encoding, and separate encoding. Sequential encoding treats both the natural language and database schema as sequences of tokens, enabling sequence-based models to capture semantic and syntactic information. Graph-based encoding leverages graph structures to represent complex relationships between input data, enhancing the model's ability to generate accurate SQL queries. Separate encoding processes the natural language and database schema independently, often used in conjunction with other strategies to improve performance. Each encoding strategy has its unique approach to transforming unstructured and semi-structured data into a form that can be processed for generating SQL queries. Figure 7 provides an overview of the primary encoding strategies used in NL2 SQL models. The sequential encoding strategy treats both natural language, NL, and database schema as sequences of tokens, enabling sequence-based models to capture semantic and syntactic information. The graph-based encoding strategy represents NL and database schema as graphs, leveraging the inherent relational structure of databases to enhance the model's performance in generating accurate SQL queries. The separate encoding strategy processes NL and database schema independently, allowing for more flexibility in handling complex relationships between the two. Figure 8 provides an overview of the decoding strategies used in NL2SQL models. It highlights three main strategies: greedy search-based decoding, beam search-based decoding, and constraint-aware incremental decoding. Greedy search is fast but may miss long-term dependencies. Beam search explores a larger search space but requires more resources. Constraint-aware incremental decoding ensures syntactically correct SQL queries by applying SQL grammar rules during the decoding process. Figure 9 illustrates an example of an intermediate representation in the context of NL2SQL translation. This representation serves as a bridge between natural language queries and SQL queries, capturing essential components without the strict syntax rules of SQL. The figure categorizes existing intermediate representation strategies into two groups: SQL-like syntax language and SQL-like sketch structure. The SQL-like syntax language approach transforms the NL query into short SQL-like expressions, bridging the gap between NL and SQL. The SQL-like sketch structure approach constructs sketch rules mirroring SQL structure for parsing, simplifying the process and improving generation quality. Additionally, the figure highlights the importance of schema linking and generation in the intermediate representation process. The post-processing strategies for NL2SQL primarily focus on refining the generated SQL to better meet user expectations. One key strategy is SQL correction, which involves correcting syntax errors and addressing keyword redundancies. This is achieved through multi-level matching approaches that expand the matching scope across columns, tables, and databases. Another important strategy is ensuring output consistency. This is done by employing self-consistency methods that sample multiple reasoning paths and use a voting mechanism to select the most consistent SQL. Additionally, cross-consistency strategies are used to diversify SQL queries while maintaining model performance. Execution-guided strategies are also crucial, where the execution results of SQL queries are used to refine the SQL. This includes processes like executable checks and beam search selections to ensure the SQL can retrieve data from the database effectively. In this section, we delve into the various types of NL2SQL datasets, highlighting their characteristics. We categorize these datasets into single-domain, cross-domain, and multi-turn types, each presenting unique challenges. Additionally, we discuss the features of these datasets, focusing on robustness, SQL efficiency, and knowledge augmentation, which are crucial for real-world applications. Finally, we analyze the complexity of these datasets through three main categories: redundancy measure, database complexity, and query complexity. This analysis provides insights into the evolution and current state of NL2SQL benchmarks. Figure 10 illustrates the evolution of NL2SQL benchmarks over time. Initially, the field focused on single-domain datasets, which were often simple and specific to a particular domain. As the field progressed, the focus shifted to cross-domain datasets, which challenged NL2SQL systems to generalize across different domains. The introduction of multi-turn datasets required systems to maintain context over interactive dialogues. More recently, there has been a growing emphasis on evaluating the robustness and efficiency of NL2SQL systems, leading to the development of datasets that simulate real-world scenarios and include domain-specific knowledge. In this section, we discuss the evaluation metrics crucial for assessing NL2SQL systems. These include execution accuracy, EX, which compares execution result sets, string match accuracy, SM, which checks for exact string matches, and component match accuracy, CM, which evaluates the matching of SQL components. We also introduce recent advancements in NL2SQL evaluation toolkits, such as MTTQL and NL2SQL 360, which handle real-world variations in NL questions and database schemas. Finally, we address the need for a standardized taxonomy for NL2SQL errors, focusing on error localization and the cause of errors to enhance model performance and robustness. Figure 11 provides an overview of the NL2SQL 360 evaluation framework, which is designed to assess NL2SQL systems from multiple angles. The framework consists of 6 core components: dataset, model zoo, metrics, dataset filter, evaluator, and analysis. These components work together to provide a comprehensive evaluation of NL2 SQL systems, focusing on the varied characteristics of SQL queries across different application scenarios. For instance, in business intelligence scenarios, SQL queries often include aggregate functions, nested queries, or top-K queries. NL2 SQL 360 allows users to use public or private datasets for systematic evaluations and to customize metrics based on specific scenario requirements. This flexibility and depth of analysis provide valuable insights into the performance of NL2 SQL systems in real-world applications. Figure 12 presents the statistics of DIN-SQL errors classified according to our proposed taxonomy. The error types include schema linking, join, group by, queries with nesting and set operations, invalid SQL, and miscellaneous. The distribution of errors shows that select errors account for 25.5%, followed by group by at 16.6%, and equality at 15.9%. This classification was manually applied to the errors generated by DIN-SQL on the Spider dataset, demonstrating the effectiveness of our taxonomy in categorizing and understanding NL2 SQL errors. Figure 13 presents a strategic roadmap for optimizing large language models, LLMs, for the natural language to SQL, NL2 SQL, task, based on data privacy and data volume considerations. The roadmap outlines how data privacy impacts the choice between open source and closed source LLMs, while data volume dictates the optimization strategies for training and inference. Additionally, the figure introduces a decision flow for selecting appropriate NL2 SQL modules tailored to various scenarios, highlighting the advantages and disadvantages of each module in different contexts. This comprehensive approach ensures that practitioners can effectively balance performance and resource efficiency when developing NL2 SQL solutions. The authors provide a strategic roadmap for optimizing large language models, LLMs, for the NL2 SQL task, focusing on data privacy and volume. For data privacy, open-source LLMs are recommended to ensure local control and prevent data breaches. Data volume influences optimization strategies such as pre-training, fine-tuning, and few-shot learning. The selection of NL2 SQL modules is guided by specific scenarios. For complex database schemas, schema linking is advised. For content mismatches, database content retrieval is preferred. And for accessible execution results, execution-guided strategies are recommended. Each module offers benefits but also trade-offs in terms of time and accuracy, emphasizing the need to balance these factors in NL2 SQL system design. The Open NL2 SQL problem involves translating natural language queries into SQL across multiple databases. This introduces challenges such as accurately retrieving relevant databases, handling heterogeneous schemas, and aggregating answers from multiple queries. To address these, a hybrid approach combining large language models, LLMs, and pre-trained language models, PLMs, is proposed, which aims to balance performance and resource efficiency. Ensuring the trustworthiness of NL2 SQL solutions is also crucial, which can be achieved through explainable AI techniques, multi-agent frameworks, and developing debugging tools that address both semantic and syntactic errors in generated SQL queries. In this paper, the authors provide a comprehensive review of NL2 SQL techniques from a lifecycle perspective in the era of large language models, LLMs. They formally state the NL2 SQL task and discuss its challenges. A detailed taxonomy of solutions is presented, based on the language models they rely on. The key modules of language model-powered NL2 SQL methods are summarized, including pre-processing strategies, translation models, and post-processing techniques. The authors also analyze NL2 SQL benchmarks and evaluation metrics, highlighting their characteristics and typical errors. Furthermore, they outline a roadmap for practitioners to adapt LLMs for NL2 SQL solutions. Finally, they maintain an updated online handbook to guide researchers and practitioners in the latest NL2 SQL advancements and discuss the research challenges and open problems for NL2 SQL. Thank you for watching.